Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 12, Lesson 3 on adding probabilities. Alright, so we've already talked a little bit about basic probability work and how sets come into play with probability. I hope you were with me for that last lesson where we did use some sets to think about probabilities and complements of events. Let's jump into it and now talk about sets a little bit more, and specifically Venn diagrams. There are times we want to determine the probability that either event A or event B happened. To do this, we need to be able to account for all the equally likely outcomes that fall into either one of the two events. Let's see how this looks given a simple Venn diagram. All right, exercise number 1. Consider the spinner shown below that has been divided into 8 equally sized sectors of a circle. The spinner is spun once. In this experiment, we will let A be the event of it landing on an even, and B be the event of it landing on a prime number. Fill in the Venn diagram below with the actual numbers from the spinner. All right, great. So let's talk about Venn diagrams. Let's talk about these two events, right? One event is we spin this thing around and we get an even. Now, just for a second, let me just kind of let's talk about what those two things are. I have no question that you have a good sense for what the even numbers are. 2, 4, 6, and 8. That's good, right? And then we've got our primes. This can kind of throw people off if they haven't thought about the primes for a while. Remember, 1 is not a prime number, but 2, 3, 5, and 7 are all prime numbers. All right. Remember, a prime number is a number that is only divisible by itself and the number 1, but we exclude the number 1 from the primes for reasons that I'm not going to get into right now, although it is kind of cool why. Anyway, so, we've got our evens, we've got our prime numbers, and I want to start to fill those numbers in here. I want to put all the evens within this circle. I want to put all the primes within this circle. And notice there is one number, right? The number 2, that falls into both of them. And I want to put that in the one location where they overlap. So that's always when I'm filling out a Venn diagram, the first thing I always do is put in any of the outcomes that fall into the overlapping region of the 2. Now the rest of this is pretty easy, right? I'm going to put the 4, the 6, and the 8 into that circle, right? And I'm going to put the 3 and the 5 and the 7 into that circle. Now there is one additional number, right? And that's the number 1. Okay? And that's the number, right, that doesn't fall in the evens and it doesn't fall in the primes. It doesn't fall in either one of them. But this is really kind of a nice way of looking at the sample space, right? Any number that falls within this circle is an even number. Any number that doesn't fall in this circle, and that's 3, 5, 7, and the 1, is not an even number. Any number that falls into this circle is a prime number, and any number that doesn't fall in this circle, its complement, is not a prime number, and that's 1, 4, 6, and 8. All right? So we can really see everything about the sample space and these two particular events, because there's other events, right? There could be multiples of 3, there could be like an event of, numbers that are odd but greater than 4, right? There's all sorts of other events we could have, but we're only thinking about these two right at this moment. All right, so let's keep going. The union and the intersection. When we have 2 or more sets, we can talk about their union and we can talk about their intersection. And these two are amazingly important concepts for the rest of this unit. So we really want to kind of understand them by taking a look at their technical definitions. So let's talk about the union and the intersection of 2 events. For 2 sets, A and B, their union, which is given by the word or, and their intersection, which is given by the word and, are given by the following. Number 1, the union, A or B, which is then symbolized, and let's come out of this for a second, right? A or B, which is symbolized by this weird kind of almost U-looking character. You can think about that as union. A or B, A union B, is all X, and X doesn't have to be a number, it's just an element, okay, of a set. All X such that X is in A or X is in B. And you can really think about this, it's a little bit harder to see, these things are dashed, as sort of just drawing one large set around all of the elements that fall in both of sets A and B, all right? So they fall in all the sets, they're either in A, they're in B, or they're in both, and it doesn't matter. Now the intersection, A and B, all right, and then we take that little U and we flip it upside down, all right, those are all the values or all the elements that are both in A and B. That is literally the overlap region, okay? So the union is take the two sets, smash them together. That's the union, okay? And those will be all the elements that are in A, or they're in B, or they're in both A and B, all right? But the intersection is literally just the elements that exist in both sets, okay? So they gotta be in A, and they also have to be in B. So let's take a look at exercise number 2. From exercise number 1, write out the following two sets, A or B, the union. All right, now again, the union is literally, I take the evens, I put them together with the primes, and we are talking about that particular set, and therefore that is literally 2, 3, 4, 5, 6, 7, 8. It is literally everything except for the number 1, right? The union of the sets A and B is everything that was in our sample space except for the element 1. Now, the intersection, on the other hand, right, this one is way more restricted, as it often is. The intersection is only the elements that lie in both of the two sets, commonly lie in both of the two sets, and that's the element 2. Now note, right, the intersection will always lie within the union, okay? The intersection will always be a subset of the union because the union is of two sets. You take all the elements in one set, you take all the elements in the other set, and you just throw them together. That's the union. The intersection, you look at the two sets and you go, what elements are common to both of those sets? And that's the intersection. Now, I like that word, intersection, right? Because when we think about, let's say, two curves, and we talk about their intersection, then we're talking about the points that lie on both curves, right? We don't typically talk about the union of two curves, but we certainly talk about the intersection of two curves, and that is the same idea here. All right. Now, very important, let's take a look at exercise number 3. From exercise number 2, why is the equation n of A or B, in other words, the number of elements in the union, equal to n of A, the number of elements in A, plus the n of B, generally not true? What would be the correct modification to make it true? Use the last example to help explain. All right, so in other words, right, let's take a look at this. Let's just look at, because this is going to be a very important equation or a very important thing to think about. The number of elements that lie in a union, okay? So the number of elements that lied in the evens were how much? It was 4 of them, all right? The number of elements that lied in the primes, that was also 4. And the number of elements that lied in the even or prime was 1, 2, 3, 4, 5, 6, 7. So we generally think about the union as adding two sets together. Why is it that when we add the number of elements in the even set to the number of elements in the prime set, we don't get the number of elements in their union? Why is that? Pause the video now and think about that. Right? And this, just to be very clear, doesn't equal 4 plus 4. And it's because of the shared element, right? It's because we count this element more than once when we add these two together, right? Now, of course, it would be easy to modify this by saying, well, I'm going to add 4, and then I'm going to add 4, and since I double counted that one, I'll just subtract 1 away, right? And then that would give me the correct answer, 4 plus 4 minus the fact that I counted that one twice. But if there were 2 of them in the intersection, right, then I would count those 2 twice, and I'd have to subtract off 2. If there were 5 in the intersection, I would have to subtract off, I would count 5 of them twice, and so I'd have to subtract 5 off. So the way that we modify this is that the number of elements that are in a union is going to be the number of elements in one set plus the number of elements in another set, and then I have to subtract out the number of elements in the overlap, right? Because these got counted twice, right? So anytime we're trying to figure out how many elements occur in the union of two sets, we have to account for the fact that we may be double counting, ones that lie in one set and lie in the other set, and so we just simply need to remove those by subtracting that overlap, all right? Subtracting out the fact that we count them twice. This gets way worse if you've got 3 events, trust me, because then you got like overlaps between 3 events and then a triple overlap. Oh, it's terrible. But at this level, you'll only have to deal with 2 events. So now we can start to talk about the probability of unions. Two-way frequency charts, which you worked back with in Algebra 1 and you'll definitely work with a lot in Algebra 2, give us a great example of how events or sets can combine, union, and overlap, intersection. Let's look at this and develop some ideas about probability along the way. Exercise number 4. A small high school surveyed 52 of its seniors about their plans after they graduate. They found the following data and wanted to analyze it based on gender. In this case, if we pick a student at random, we can place them into one of 4 events: male, female, going to college, not going to college. And I do want to give a little nod to those students who might not identify as either male or female. Eventually we will get that kind of worked into these surveys, all right? But for right now, we're going to deal with every student in these surveys as being sort of, gender identifying as either male or female, all right? And going to college, not going to college. So when we look at this particular table, right, we can see it all kind of broken down into these various categories. So let's start to do some counts on that. Let's take a look at letter A. Give the values for each of the following. The number of people that fall in the male category. All right, well that's really easy because, we've got 16 males that are going to college, 14 males that are not going to college. They've even totaled this for us. Sometimes they don't give you the totals. You have to do that yourself, which is annoying. But in which case, right, there are 30 that fall into that category. All right? Now, right, all 3 of these are going to be pretty easy. So what I'd like you to do is take a moment to figure out n of f, n of c, and n of n, I guess. Pause the video now and go ahead and do that. All right, the number of those who were surveyed that were female is 22. Again, they've totaled those for us. The number of those surveyed that are going to college are 29. The number of those surveyed not going to college are 23. Again, they've gotten all those totals for us. Now we start to get into some intersections and some unions, right? So in part 5, the number that are men and college, right? Now again, what's kind of cool about that is that going to college, right, is this set, being male is this set, and so you can see right away that the intersection, which is what we're looking for when we're talking about an and situation, is 16. Now, you don't really even need to know the terms intersection and union to say, well, if I want the number of men and going to college, that's 16, right? Simple enough. Now, in 6, right, the number that are female and going to college, right? That's going to be easy enough, right? We go over here, female going to college, and that's 13. But the hardest one probably is the last one, female or going to college. And let me get rid of all of this so we don't have that all, oops. And of course I just erased the 29. Female or going to college. Now that's a little bit tricky, right? Because here are all the people that are female. Here are all the people going to college. So it would be very, very tempting, right, to do something like this, to say, well, I've got 22 that are female, and I've got 29 that are going to college. The problem, of course, in that situation is that you would be counting these 13 people twice, right? Because you counted them as you went across here, and you counted them as you went down here. That's easy enough. All we have to do is then subtract off the fact that we counted them twice. And that's easy enough then to just say, well, we've got, let's see, that'd be 51 minus 13, which is 41. And that's 38. Yes. All right. Now, I get it. I totally do. I'm sure that there's some of you out there that say, well, look, I don't need to do 22 plus 29 minus 13. I just have to keep careful track, right? I'm just going to say, well, I've got 9 plus 13, that gives me the females, right? I've got the 16, the 13, which gives me the people going to college, but I counted that one too many times. So all I would have to do, right, is add my 9, my 13, and my 16, and to ensure that I'm not counting anything twice. Totally nothing wrong with that, go for it, right? But this is a formula you're supposed to know. In other words, the number of elements that are in a union of two sets is the number of elements in one of the sets plus the number of elements in the other set minus the number of elements that are common to both sets, because that 13 lies in both the 22 and the 29, so it's counted twice. Now, let's take a look at letter B. Yeah, that's right. We're all the way to letter B now. What is the probability that a person picked at random would be a female who is going to college? Represent this either using a union or an intersection. All right. So in other words, right, when we see something, the probability picked at random would be a female who is going to college, right, we actually are looking for female and college. And there's no fancy formula we need for this, right? We simply take a look and we say, okay, there are 13 people that are female and going to college, right? That's the intersection, out of a total of 52 people. So 15 divided by 32. 13 divided by 52. I love the fact that I just said 15 divided by 32. Neither one of those numbers is up there. So 13 divided by 52. You know, my problem is, like, I'm thinking about cards and a deck. I'm thinking 13 divided by 52 reduces to 1/4, and I don't know. Anyway, not a great excuse, but true. All right, letter C. What is the probability that a person picked at random would be a female or someone going to college? Represent this using either a union or an intersection. All right, and again, now it's very straightforward, female or going to college, so that's the probability of female or college. Now that's going to be the number of people that fall into that union, which is 38, that's right from here, divided by 52. Okay, so let's take a look at letter D. Explain why the probability of female or college, the one that we just got, is not equal to the probability of female plus the probability of college. Well, again, notice what we just got, right? Probability of female or college was 38/52, but the probability of female would be 22 out of 52. And the probability of college would be 29 out of 52. Clearly, if I added this plus this, I wouldn't get that, right? And again, same song, second verse, because some people fall in both categories. Specifically, right, the people, right, who are right here, right? The people who fall into the category female and college get counted in this, and they get counted in this, and so those two added together don't equal that. But now we can come up with a probability formula based on our count formula, right? So let's take a look at letter E. Fill in the general probability law based on D. All right, so we know that the probability of A or B is going to be the number of people in A or B divided by the number of things in our sample space. We know that. All right. Now, we also know the number of people in A or B is the number of people in A plus the number of people in B minus the number of people in A and B. I cannot believe I can't fit that in, all divided by n of s. Sorry about that. All right, let me be very clear about what's written right here, since you probably can't read that on your screen. Right, so that was that formula that we just developed on count. But we can divide everything by this n of s. Specifically now, we can say that the probability of A or B is equal to n of A divided by n of s plus n of B divided by n of s minus n of A and B divided by n of s. And finally, I can now say, right, that the probability of a union is the probability of event A plus the probability of event B minus the probability of the intersection. Right? So if I know the probability that one event will happen, and I know the probability that the other event will happen, and I know the probability that they'll happen at the same time, their intersection, then I can find the probability that either or happens by adding the two probabilities of the two individual events together and subtracting off the overlap probability, right? It's exactly the same as the count, right? We're going to add too much probability here, so we have to subtract off the probability of the overlap. Now again, you might say, well, in a situation like this, that would be no problem for me, because if I'm trying to figure out the probability that it's either a female or someone going to college, then I'm going to first account for maybe, let's say, all the females, 22 of them. Then I'm going to look at the people going to college. I've already counted this 13, so I'm not going to worry about that. So I would just take the 22, add the 16, I'd get 38, right? And I'd get 38 out of 52. And I never want to invalidate something like that, all right? So that's a fairly good approach, nothing wrong with it. But sometimes it's hard to get away from that particular formula. Now, sometimes we can avoid the probability law that we encounter in the last exercise by simply keeping careful track of what elements of the sample space are in both of our sets and making sure we don't count any element twice. And let's look at a very easy example of that in exercise number 5. A standard 6-sided die is rolled once, so easy peasy, right? Find the probability that the number rolled was either an even or a multiple of 3. Represent this problem and the sets involved using a Venn diagram. Even though you don't need it, verify the probability addition rule from exercise 4E. All right, great. All right, so obviously, right, our sample space is going to be 1, 2, 3, 4, 5, 6. All right, we've got evens, and we'll get to the Venn diagram in a second, which are 2, 4, 6. I'm going to use m for multiples of 3. Those are 3 and 6. Okay. So we can represent everything kind of going on here with our nice sample space, right? We've got our evens. We've got our multiples of 3. Do we have an overlap? Sure we do. That's our number 6. Now the other numbers that are in there are evens, are 2 and 4. The other numbers in our multiples of 3 are, well, 3, right? We have 2 elements that are sitting outside of there, 1 and 5. So I'll just kind of have them hanging out there. They're not going to even play in this game. Okay. Now, if I want to know the probability that I'm going to roll either an even or a multiple of 3, well, there are 6 total outcomes in my experiment, right? That's my sample space. 4 of them lie in here. So the probability of even or m is going to be 4/6. Now, that's very simple, right? It's very, very easy, okay? Because I didn't count the 6 twice because I didn't have to. I could just look at my diagram and go, oh, 1, 2, 3, 4 lie in my union out of 6 total, so 4/6. But check this out, right? You know, the probability that I would get an even, that's going to be 3/6. The probability that I have a multiple of 3, that's 2/6. And the probability that I would get, the probability that I would get an even and a multiple of 6 is 1/6, right? So if I just said, well, I'm just going to add these 2 probabilities together, which would be understandable, that would give me too big of a probability. 3/6 plus 2/6 would be 5/6. But if I then subtract off that 1 extra one, right, then I've got 5/6 minus 1/6, and that's 4/6, right? The probability of evens plus the probability of a multiple of 3 minus the probability that the number rolled was both even and a multiple of 3 gives me the correct answer. Now again, if you're the kind of person that says, I'd never do it this way, I would just kind of think about it. Okay, I got 2, 4, 6, that's one category. I got 3 and 6, that's the other category. 4 total numbers fall into one or the other, right? They're union, great, 4, 6, awesome. But let's take a look at one that isn't so easy to sort of avoid. There are some situations where the probability addition rule is harder to avoid. Exercise number 6. Insurance companies typically try to sell many different policies to the same customers. At one such company, 56% of all the customers have car insurance policies. 48% have home insurance policies, and 18% have both. A customer is picked at random. A. What is the probability that she or he has at least one of the policies? All right, and really what this is saying, right, is what is the probability, right? So what do we have? We have car insurance, home insurance. So, right, we know the probability of car insurance is 0.56. The probability of home insurance is 0.48. And please note, right, they did not say 50% of the customers only have car insurance. They didn't say that. 56 out of 100 people have car insurance. 48 out of 100 people have home insurance, and 18 out of 100 have both, right? So the probability of somebody having both car and home insurance, right, is 0.18. And you can really, if it's helpful for you to think about it as, look, there's 100 people, right? And 56 of them have car, 48 have home, and 18 have both. Awesome, right? So to have at least one, right, to answer that question, to have at least one is saying, what is the probability that they have car or home insurance? All right, and for this, it's harder because we don't have some table, we don't have a die that we're throwing, right? So we can think about these people, right? We could take the 56 people that have car insurance, add 48 people that have home insurance, but that would be 104 out of 100 people that have one or the other. And of course, the reason why that's wildly unrealistic is if we're thinking about 100 people, then that's too many, right? And that's because we've counted these 18 people twice. Again, this is like thinking about 100 people, right? And it's a good way to think about percentages. So what do? Well, we simply take 0.56, we add to it 0.48, and we subtract off 0.18, and we find that we must have 0.86 or 86% have at least one of them. Either way. All right. Now let's take a look at letter B. Find the probability that she or he has neither of the policies. Pause the video now. See if you can figure that one out. Well, that is the complement of what we just found, right? So this is the complement of the event in A. So the probability neither is 1 minus the probability of at least 1, which is going to be 1 minus 0.86, and that's 0.14, or 14%. So 14% of all the customers don't have either car nor home insurance. All right, let's move on. So let's wrap this up, right? Today, we learned about two very important ideas, not just for probability, but for set thinking in general. The idea that if you have two sets, which are just collections of collections of elements, right? We can merge those two sets together and we have what's called the union, really saying that an element is in either A or B or both, all right? And the word or in the English language almost always implies that you're in one of them or the other one, but you're not in both. When you talk about the word or in math, it's what's called an inclusive or, which means you could be in one of them, the other one, or you could be in both of them. So that's the union, and that's typically thought of as the word or. Now, you also have, though, all the elements that are common to both sets. That's what's known as the intersection of two sets. And both the union and the intersection are very important in probability thinking because we oftentimes want to calculate the probability of the union of two events. So what is the probability, right, that the number rolled was either, an even or a prime number, or an even or greater than 4, something like that, right? When you do that, right, you want to know how many fall in one set, how many outcomes fall in the other set, but then you have to be wary of their intersection because the intersection will always be counted twice if you're either doing a count or if you're doing a probability. And so we developed these two general rules that are, of course, more or less the same rule, which is the number of elements that are in a union are equal to the number of elements in one set plus the number of elements in the other set minus the number of elements that are in the intersection of the two sets. When we bump that up to probability, we say that the probability of event A or event B is equal to the probability of event A plus the probability of event B minus the probability that event A and B occurred at the same time. Now again, a lot of times those kind of probabilities can be done by just careful counting and thinking about the scenario at hand. Other times, like in that last problem with the insurance, you really have to know that formula. Otherwise, you'll have no idea really what to do. All right, we'll see this more in our next lesson. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.